Hello everyone, my name is Anudh Mishra and I am an MBBS student at AIIMS Bhuvneshwar. Today I'm going to discuss about the chapter surface chemistry. This is a very easy chapter belonging to your physical chemistry of class 12, and there are only very few concepts which we need to understand in this chapter to solve the questions. Today we are going to cover the adsorption part and catalysis part, and in the next class we'll cover colloidal solutions. Okay, so let's start with the definition of surface chemistry and what it deals with. So it deals with all the phenomena that occur at the interfaces or surface. So the interface, what is an interface? It is a medium or a it is a line which separates two different kinds of things. Okay, that is an interface. So you can define it by saying that it separates two things, or it is the junction of two different media. Okay, two different bulk phases, two different media, right? So interface between solid and gas. Uh, there is no interface between gases, but there are interfaces between solids and liquids and gas. Okay, the interface is normally a few molecules thick, but its area depends on the size of the particles of the bulk phases. So what I'm saying is, if the particles are small, so it might contain lots of molecules. But if the particles are large, so it will contain much fewer number of molecules. It is basically a relative term. Okay, moving on. Uh, the most noticeable phenomena NCRT says is corrosion, electrode processes, heterogeneous catalysis, dissolution, crystallization. All of this occur at interfaces. Yeah, it might be a little bit difficult to believe all of that, but yes, all of these phenomena are surface phenomena or interface phenomena, including corrosion, electrode process, heterogeneous catalysts. Today we'll start with adsorption and move on to catalysis. Before that, I want you to know that we'll be solving PYQs in the end. Okay, let's start with adsorption. So what is adsorption? I'll tell you the difference between adsorption and absorption. Okay, suppose this is the surface. So what happens in adsorption is molecules tend to get accumulated on the surface in adsorption. Okay, they are present only at the surface. Although the concentration might vary, but they are not present in the bulk of the matter. Okay, but whereas in absorption, they are present, they penetrate the matter basically. You get what I'm saying? They penetrate the matter completely in absorption. See, in adsorption, they are present at the surface. Okay, they cannot go or they do not go inside. This is how it looks like. If you just look at a gross picture. But in absorption, apart from the surfaces, they are also present in the matter. We all know what absorption means. We have been using that term since long time. This is the absorption is very uninteresting process. Adsorption is what we are concerned here, and let us see how adsorption is interesting and what it tells us. So, the accumulation of molecular species at the surface rather than in the bulk of a solid or liquid is termed adsorption. So, the accumulant or with a substance which is accumulating on the surface is known as adsorbate, and the material on the surface of which the adsorbate is getting accumulated is known as adsorbent. What is peculiar about it? This is usually, although usually adsorbate is a gas and adsorbent is a solid, but we frequently see other examples where, for example, the adsorbate is a liquid and adsorbent is a solid, or adsorbate is a gas, adsorbent is a liquid, or even adsorbate is a solid, adsorbent is a liquid. So there are varied examples. Don't assume that only a gas is adsorbed over a solid. Adsorption is surface phenomena. Solids have a large surface area in finely divided state, and therefore charcoal, silica gel, alumina gel, clay colloids, metals in finely divided states are good adsorbents. Right? What do you have to remember is adsorption depends on the surface area. And if you take a metal chunk like this, it has got only this much surface area. But if you divide it into thousands of chunks, you will have so much, so much, so much, so much, so much, so much surface area. Got it? So metals in finely divided states are good adsorbents. Adsorption in action, some practical examples which usually come as questions. Okay. Don't miss any point in chapters like these, because these usually don't contain a lot of numericals. So these small one liner points can come as questions in JEE Main. And you should not miss these questions because they are easy to score. Okay, you just have to read the NCRT completely. First example is, if a gas is taken in a closed vessel containing powdered charcoal, it is observed that the pressure of the gas it decreases in the vessel. Why? Because the gas molecules concentrate on the surface of charcoal. Similarly, a solution of an organic dye with animal charcoal, the filtrate turns colorless because molecules of the dye accumulate on the surface of charcoal. Third example is, aqueous solution of raw sugar passed over animal charcoal becomes colorless as the coloring substances are absorbed by the charcoal. So what the thing happens is, see why charcoal is so good at adsorption. What is it made up of? Suppose you take a wooden log. This is a wooden log, and what do? You turn it to charcoal or burn it. So it turns into a block of charcoal. So you have burnt it. It has a carbon skeleton remaining, but most of the carbon has escaped, forming CO2, right? So what happens is, the escaped CO2 creates pores in the micropores, not this big pores. I'm just showing it for reference. Creates micropores on the charcoal surface. So the surface kind of looks like something like this. And if there is a straight surface and there is a surface like this, of course, this surface has more surface area. So it can accommodate a large amount of gas. That is why charcoal gas or dye or whatever. That is why charcoal can absorb so much, so many substances. Got it? Last example says air becomes dry in presence of silica gel. Why? Because silica gel absorbs the water on its surface. Okay. Now, the reverse process of adsorption is desorption. Distinction between adsorption and absorption. This is, I've already told you. We'll just see an example here. When a chalk stick is dipped in ink, the surface retains the color of the ink due to adsorption. Whereas the solvent of the ink goes deeper into the stick due to absorption. On breaking the chalk stick, it is found to be white from inside. So ink has been absorbed, water has been absorbed. Okay. Both adsorption and absorption take place simultaneously also, but the term sorption is used to define both the processes. Okay. Which means that if there is a molecule, both absorption has occurred and adsorption has occurred. This will be defined as sorption. Okay. Then mechanism of adsorption. Why are molecules actually coming and getting attached to the surface? What is so special about the surface of any of these adsorbents? So the thing is, we have learned in surface tension. On the surface, the molecules don't have anything to pull them up. Okay. They can only be attracted down by the molecules which are below them. Okay. All the resulting forces come like this. So if I draw a more clearer picture, this is a surface. These are the molecules in the study. They have a force of attraction towards the interior, whereas the interior are having no force of attraction because they are equally being attracted from all sides. So they are having no forces of attraction. So a surface molecule has a inward force of attraction. Now if some molecule comes and gets stuck here, it can get attracted, right? Because there is an inward force of attraction. So this red molecule has been attracted. That is why adsorption is so feasible at the surface. See, surface of the particles are not surrounded by atom or molecule on outside. They possess unbalanced or residual attractive forces. These forces of the adsorbent are responsible for attracting the adsorbate particles. Okay. Extent increases with increase in surface area per unit mass and temperature and pressure. These 3 points: surface area, per unit mass, temperature, and pressure. Then there is something called the heat of adsorption, something which relates it with thermodynamic. Nothing. If something is getting attracted and they are coming together, suppose two particles are coming together, so their potential energy will decrease, right? So some heat will be released. This heat released on adsorption is there is decrease in the surface energy which appears as heat. This is called the delta H of adsorption, and it is always negative. Okay, so we have also defined the heat of adsorption, enthalpy of adsorption. Now there are two factors in the in the equation of free energy. See, delta H is negative for all, and delta S will be what? Again negative, because entropy is decreasing. Because what is happening is, that some gas molecule was roaming here and there. It had a randomness, but now it is stuck to a surface. So delta S is negative. Got it? Why delta S is negative? Entropy has been decreased. So how to make this delta G minus? Because if delta G is negative, then it is spontaneous. And we know absorption is spontaneous. So if this is negative, this negative turns this whole thing into positive. So T has to be less. T should be very, very less. So thus spontaneous adsorption combination is required, and you know you need a low temperature, and it is inversely proportional to temperature, right? Then there are types of adsorption. So mainly two types: adsorption of gases and solids. Okay. It is physical adsorption or chemical absorption. Here we are only talking about adsorption of gases on solid. Okay. Physical adsorption is also termed as physisorption, chemical absorption as chemisorption. Now, what are the features of physical adsorption? So, if we see the characteristics of physisorption, it has some peculiarities. What? There is lack of specificity. Okay, it does not have preference for any particular gas. It has a dependence on the nature of adsorbate. Okay, the amount of gas adsorbed depends on the nature of the gas. Easily liquefiable gases are readily adsorbed as van der Waals forces are stronger near the critical temperature. So, 1 gram of activated charcoal absorbs more sulfur dioxide than methane, which is still more than dihydrogen. So, SO2 is absorbed more than methane, which is absorbed more than dihydrogen on 1 gram charcoal. Why? Because SO2 can be easily liquefied. What does it mean? That molecules of SO2 have affinity towards each other, but molecules of hydrogen do not have affinity, that much of affinity towards each other. So if they have affinity towards each other, they will tend to stay stable when they are present near each other in a adsorbed state, which is like not possible in a hydrogen molecule. They will repel each other. They're not stable together. They want to stay far apart. Okay, so nature of adsorbate, critical temperature and all these you need to know here. Then physisorption is reversible. Okay, you just heat it or you decrease the pressure to remove the gas from the surface. And if you want more adsorption to occur, more of gas is absorbed when pressure is increased. Okay, Lechat clears. And uh, low temperature, all these are for increasing adsorption. Surface area definitely depends on surface area. Enthalpy of adsorption is quite low. It is not that stable. So that is why in simple heating you are getting back the reactants. So this was physisorption. Why is physisorption occurring at all? See, what the thing is, we need to remember here is that physisorption has only physical forces which are attracting the adsorbate. Okay. There are no chemical forces attracting the adsorbate. So there is no affinity between the two phases. So some gas is getting adsorbed on the metal. Gas and the metal are not interacting with each other. It is just because of the unbalanced attractive forces at the surface that the gas molecule is being attracted there and getting adsorbed. Not because there is some real chemical adherence or some chemical relation or chemical attractiveness towards the solid by the gas. So gas and solid don't have any affinity, but still, due to physical forces, they are getting attracted. Now comes chemisorption. Essentially the reverse. Here, there are physical forces tending to do adsorption, but dominant ones are the chemical forces. So the adsorbate and adsorbent have chemical bonds with each other here. Okay, because it is chemical, so there is high specificity. For example, oxygen is adsorbed on metals by virtue of oxide formation, and hydrogen is absorbed on transition metals due to hydride formation. So oxygen is adsorbed on metals. Why? Because it forms oxide there. It is irreversible because it is chemical process, so it is irreversible. It is an exothermic process, but very slow at low temperatures because it has, this is an important point, it has high energy of activation, a relevant thing which we should remember. All right, enthalpy, will directly jump to enthalpy. It is high, 80 to 240. It involves chemical bond formations. Again, it depends on surface area. Let us see some direct differences. Physisorption is due to van der Waals forces, chemisorption due to chemical bond. Physisorption non-specific, reversible, chemisorption specific and irreversible. Physis option depends on the nature of gas. It depends on the nature of gas. Again, gases which can react, only they can be chemi-absorbed, or here in the physis option, liquefiable gases are absorbed readily. Now enthalpy is low in physi, enthalpy is high in chemi. Then low temperature is favorable for physis option, high temperature is favorable for adsorption, but not too high. Enough to achieve activation energy. Only that much heat is required. Now, no appreciate, no activation energy is there. Here, high activation energy is there. Then in physis option, surface area again. Here also it increases with surface area. Chemis option. Physis option is a multimolecular layer. Chemis option is unimolecular. We can essentially guess that physis option, like attraction is there, no? So multimolecular layers will be formed. But in chemis option, it is a chemical bond formation. So you can see just there's a unimolecular layer. Then there is adsorption isotherms. Just remember this equation, Freundlich adsorption isotherm equation. The X is the mass of the gas adsorbed on mass M of the adsorbent at pressure P. K and N are constants. Okay. N should be more than 1 here. Taking log, and you can plot the log also. Okay. So the intercept, or this here log K is the intercept. Slope is 1 by N. Okay. So the slope or factor 1 by N can have values between 0 and 1. Okay. Then N 1 by N is equal to 0, X by M is constant. Adsorption is independent of pressure, but when 1 by N is equal to 1, X by M is equal to K, and it is directly proportional to pressure. So yeah, pressure variability is, so N is pressure effect. Solids can adsorb solutes from solution also. This is called adsorption from solution phase. Example is acetic acid in water shaken with charcoal. Part of the acid is adsorbed. Now, observations. The extent of absorption decreases with increase in temperature. Again, temperature increases, adsorption decreases. Now, again, it increases with increase of surface area. It depends on the concentration of solute in the solution and depends on the nature of both. Just here, instead of pressure, you take the concentration in the Freundlich isotherm curve and you get almost the same log curves, and it is similar to the pressure wala curve. Here only pressure is there. There you have used concentration. Applications of adsorption: high vacuum you can produce by adsorbing additional gases left. Gas marks. Gas marks usually use charcoal to adsorb poisonous gases. Then control of humidity, silica and aluminum gels. Adsorb water, removal of coloring matter. We just saw animal charcoal removes color matter. Heterogeneous catalysis, we'll see it. Separation of inert gases, curing diseases. Drugs kill germs by getting adsorbed on them. Froth flotation process, you'll read it in mineral. Adsorption indicators, okay? So silver halides that have the property of adsorbing dyes like eosin fluorescent have the produced characteristic color at the end point. Then chromatographic analysis. Again, chromatography is based on adsorption because this is the chromatographic paper. The solvent or solute will get adsorbed and to a various different degrees. Okay, some will get here, some will get till here, some will be left here. That is preferential adsorption is shown to separate the molecules. Okay, catalysis. Before we move to catalysis, some points: what an enzyme is, what a catalyst is. Enzyme and catalysts are not, like, all enzymes are catalysts, but all catalysts are not enzyme. So remember that enzyme is a catalyst in a biological system, biocatalyst. Now, what do these catalysts do? Okay, they accelerate the rate of reaction. Okay, they do not get changed themselves. We will just, okay, the promoters and poisons. Okay, there are catalysts Then there are promoters and poisons. So promoter and poison are the ones which affect the catalyst, not the reaction. Catalyst affects the reaction. Promoters increase the function of catalyst, poisons decrease the function of catalyst. Examples have been given here. In Haber's process for manufacturing ammonia, molybdenum acts as a promoter of iron, which is used as a catalyst. Then catalysts are homogeneous or heterogeneous? Okay, so homogeneous catalysts are, they have the same phase of the reactant. So if you are seeing two gases reacting with each other, the catalyst will also be a gas. Okay. Examples they have given: oxidation of SO2 and SO3 with oxygen in presence of nitrogen oxides. Then second example is liquid catalysis. Here methyl acetate is catalyzed by H plus ions. Okay, the hydrolysis of methyl acetate. Now hydrolysis of sugar is catalyzed by H plus ions furnished by sulfuric acid, again aqueous or liquid state. Then comes the heterogeneous catalyst. This is explained with the use of adsorption theory. Okay, we will see adsorption theory of heterogeneous catalysts. We will see what this theory says. But before that, we'll just go to the different examples. Okay, first example is SO2 oxidation to SO3 in presence of solids platinum. Next is again Haber's process. All of them are gases except iron, which is a solid. Okay. One more example is oxidation of ammonia into nitric oxide in the presence of platinum gauze in Oswald's process. This is used in manufacture of HNO3. Okay. One more heterogeneous catalysis is vegetable oils. Nickel solid is catalyzing the oxidation of vegetable oil into vegetable ghee. So we have covered the example of both homogeneous and heterogeneous catalysis. Point of interest here is the heterogeneous catalysis because it can be explained adsorption. So here we come to adsorption theory of heterogeneous catalysis. It says that catalysis is due to adsorption of reactants on the surface of catalyst. So what it basically says is this is the surface of catalyst. In the absence of catalyst, reactants are randomly moving here and there, okay? But they are getting collided very few and turning into product. But here they're getting adsorbed. Here they are getting adsorbed on the surface and instantly turning into product because they are being brought together by the surface of the by the virtue of the surface of catalyst. So yeah, let's see the mechanism. First, the diffusion of reactants to the surface of catalyst. Reactants diffuse and reach the surface. They get absorbed. Then chemical reaction occurs. They desorb. Okay. They make the surface available again for more reaction to occur. Then they diffuse away from the catalyst surface. So these are the steps which you need to remember. All right. The surface of the catalyst, unlike inner part, has free valencies which provide seat for chemical forces of attraction. When a gas comes in contact with such surface, molecules are held up there with loose chemical combination. If different molecules are adsorbed side by side, they may react. That is what happens. By chance, two reactants come together, they react and form the product. Okay, because they are basically it is bringing the reactants together. Okay. This theory explains why the catalyst remains unchanged in mass and chemical composition at the end of reaction. Because it is not being used. It is just giving the surface for reaction to occur. Why it is effective even in small quantities? Because only a small quantity of catalyst can give a huge surface area for reactions to occur. Okay. Important features of these solid catalysts. What are the important features? Firstly, the activity. Strength of chemisorption. Okay. That is how active they are. Selectivity. There is high selectivity. Okay. For example, the same reaction with different catalyst produces different products. So each catalyst is highly selective to what kind of reaction it will catalyze and what kind of reactants and products it is going to interact with. Very simple basic points, just need to read it and examples and all. Then shape selective catalysis, what they are called zeolites. They are catalysts that select their reactants based on the shape because they have some pores. They are microporous aluminosilicates with three-dimensional network of silicates. Some silicon atoms are replaced by aluminum atoms, and they have pores and cavities. So size and shape of reactant is important. Okay. Examples are in petrochemical industries for cracking of hydrocarbons. Okay. Example is ZSM5. It converts alcohols to gasoline or petrol. So all this example is important. ZSM5. Then let's move to enzyme catalysis, which I was telling you in the beginning. It is a any biocatalyst is known as your enzyme. What is enzyme catalysis? Enzyme catalysis, just nothing in a biochemical process. They catalyze reactions. Just need to remember examples. Inversion of cane sugar, invertase is the enzyme. So yeah, something you need to remember. They are proteins mostly. Okay, mostly they are proteins. Then conversion of glucose to ethyl alcohol. Okay, this is seen in. I'll just see underline the enzyme and then I'll give examples. Then conversion of starch to maltose, conversion of maltose to glucose. Let's cover this much first. Inversion of cane sugar. It happens in your intestine. Conversion of glucose to ethyl alcohol, yeast. So this is how they produce alcohol. These two reaction for digestion, they are important. Okay. Now decomposition of urea into ammonia and carbon dioxide. Urease. So this is done by bacteria. Then in stomach, the pepsin enzyme converts protein and peptide into and then proteins into peptides, and in the intestine, pancreatic trypsin converts protein into amino acids. Convert milk into curd by lactobacilli enzyme. So this is the table of enzymes and the reaction. Again, some characteristic of enzyme catalysis: efficient. They are really efficient. They can catalyze millions of molecules per second. Specific, active under optimum temperature and optimum pH. So these two are important. So if you draw a graph, this will be something activity with temperature or pH. So you will see that max activity is at a optimum pH or temperature. Okay. Then their activities increase in presence of activators and coenzymes. So coenzymes are small non-protein and present along with an enzyme and increase its activity. They are called coenzymes. For example, vitamins or ions such as sodium, manganese, okay, potassium, calcium. A good example is amylase is very active in presence of sodium ions. Then for activators, there are inhibitors and poisons. So they are some examples like inhibitors and poisons interact with the active functional groups of the enzyme surface and reduce the or destroy the catalytic activity. So drug action is mainly an example. Mechanism of enzyme catalyst. Again, it is a lock and key mechanism. This is the enzyme with E. We have the substrate. Substrate fits into the enzyme. Okay, lock and key concept. Substrate fits into the enzyme. Enzyme breaks the substrate into products. So yeah, binding of enzyme to substrate, enzyme substrate complex, decomposition to form enzyme and product. Then they have given industrial catalytic processes, Haber's, Ostwald's, contact processes. You need to just look at them once. So yeah, we are done with catalysis. We will move to the questions. In the next class, we'll see colloids. Number of statements which are characteristics of physisorption are. It is highly specific. Physisorption is not specific. Enthalpy of adsorption is high. It is not high. It decreases with increase in temperature. Definitely, it is exothermic. So, if you increase temperature, less adsorption will happen. It results into unimolecular layer. No. No activation energy is needed. It is true. Just a second. Hmm. Let's move on to the next question. We have number of incorrect statements. Water and vapors are absorbed by anhydrous calcium chloride. So this is the correct statement. Yeah, calcium chloride adsorbs. There is a decrease in surface energy during adsorption. Definitely, it is released as heat. As the adsorption proceeds, delta H becomes more and more negative. It is not true. See, as the adsorption proceeds, delta H becomes more and more negative. If it is they are saying enthalpy change is becoming negative, which means they are implying that the enthalpy is steeply declining. Okay, enthalpy is steeply declining, something like this. I don't think that if you start adsorption once, that it will facilitate more and more absorption. I don't think that happens. So I will go with C. Hmm, okay, here we have an assertion and a reason. Assertion says in expensive scientific instruments, silica gel is kept in watch glasses or in semi-permeable membrane bags. Why? Reason says silica gel absorbs moisture from air via adsorption that protects the instrument from water corrosion and prevents malfunctioning. So yeah, we can see that this is both the statements look true and reason is correct. Reasoning is correct. So we'll go with yeah, both A and R are true and R is the correct explanation of A. Now log x by m versus log p for adsorption process is a straight line inclined at an angle of 45 degrees. See, your friend Lynch isotherm has come. Intercept is equal to this. Intercept is what? Log k. And angle is 1 by n. Tan 45 is equal to 1 by n. The mass of gas adsorbed per unit mass of adsorbent at pressure 0.4 atm. Okay, so basically what they're saying is log x by m is equal to log k, they have given 0.6020. So k is equal to antilog of 0.6020. That is k is equal to 4. This we can say angle of 45 degrees. So 1 by n is equal to tan 45, tan 45 is 1. So m is equal to 1. Now x by m is equal to k p to the power 1 by n, right? They have given k as 4, they have given 1 by m as 1, they have given pressure as 0.4. So 0.4 is equal to, sorry, 0.4 into 4 is equal to the mass of gas absorbed, that is x by m. And this is at ATM, which is equal to 10 to the power 5 bar, which is the SI unit. So this comes as 1.6 something, and which is equal to 16 into 10 to the power minus 1. So this is 16. Now adding surfactants and non-polar solvents, this is not, this is colloids. Right. Amongst the session, amongst helium, neon, argon, and krypton, 1 gram of activated charcoal absorbs more of krypton. We can see tendency to liquefy is more in large molecules because of van der Waals forces more. So yeah, krypton is the largest of them. So this assertion is correct. Now critical volume and critical pressure is highest for krypton, but the compressibility factor is lowest for krypton. So compressibility factor at critical point is lowest for krypton, which means it can't be compressed, but critical volume and critical pressure are highest for krypton, which means at critical temperature, when it can be liquefied easily, the volume is really high, P is also really high, which implies that it is less liquefiable, which I don't think is true. So assertion is true, but reason is false. Then again, we get Friendlich isotherm. The slope is 3, intercept is 2.505. Okay, the value of 1 by n and log kr. So 1 by m is equal to 3 and log k is 2.505. So yeah, this is the answer. Okay. Question says, for physisorption, dash decreases with increase in temperature. Yeah, physisorption decreases with increase in temperature. No appreciable activation energy is required. Okay, we are just looking at the solutions. We'll move to the next one. Sorry. Yeah, one more adsorption question we have. Methane is adsorbed on 1 gram charcoal following Friedrich isotherm. 10 ml of methane is adsorbed at 100 mm of Hg. 15 ml is adsorbed at 200 mm of Hg. Volume of CH4 adsorbed at 3 mm of Hg is 10 to the power x ml. Value of x is. So adsorbed on 1 gram charcoal, right? So x by m. M is equal to 1 gram. X is variable. The thing is, 10 ml is adsorbed at 100 mm of Hg pressure. 15 ml is adsorbed at 200 mm of Hg pressure raised to the power of 1 by n. All right. They are asking 300 mm of Hg. The volume of CH4 adsorbed at 3 mm Hg pressure. So V, we'll take the volume as V, and here we'll put 300, 1 by n. Taking the ratio here, we have 2 by 3 is equal to 1 by 2 to the power n. So 1 by 2 to the power n mm, log 2 and log 3 they've given. Taking log on both sides. Log 2 minus log 3 is equal to minus n log 2. So this will be 0.17 is equal to n into 0.3. So n is equal to 0.17 by 0.3. This is the value of n, right? Now we divide this by the we divide both of them and we see what it comes. We'll divide it by the first one, 10 1. So 10 by v is equal to 1 by 3 to the power 1 by n. Let's take log on both sides. Log 10 is 1 minus log v is equal to oh sorry, we have taken some calculation error has been done here. It was 1 by n. Okay, 1 by 2 to the power 1 by n. So 0.17 is equal to 1 by n into 0.3. So n is equal to 0.3 divided by 0.17. That is the value of n, and we put this in the other equation, that is 1 minus log v is equal to minus 1 by n into log 3. Log 3 is 0.47. Value of n is 0.3 into 0.17 into 0.47. So we have 0.3 plus 0.17 into 0.47 is 0.08 from 0.3. So 0.38 divided by 0.3 is 1.26. So log v is equal to 1.26. That is about, I think, 6 2s are 12. Mm, see, it is like 0.4, 0.8. So 3 and 6. It is about, I think, 18. And x is 18 ml. So 18 ml is 10 to the power x ml. Yeah, we just have to take 1.26, right? They have asked us in terms of log v. So yeah, log v or v is equal to 10 to the power 1.26. That is 12.126 into 10 to the power minus 2. Yeah. So yeah, we have solved it. See, select the graph that correctly describes adsorption isotherms at T1 and T2. T1 is more. So the graphs will be x by m with p. So x by m is equal to kp to the power 1 by n. So yeah, it is exponentially. So yeah, the slope will definitely be more for the one with lower temperature. So this is going to be the answer. It won't be a straight line because it is some kind of parabolic function. Now Tyndall effect and all we leave. Given below, negatively charged. Adsorption question, one more. Correct for adsorption. Delta H is negative, delta S is negative. Third one is correct. We just saw it. Now, moving to the next. Hmm. Colloid drug enzyme interaction. Non-competitive inhibitor binds to the allosteric site. What is non-competitive inhibitor? Which won't compete with the substrate. So if this is the enzyme, this is the substrate. Non-competitive inhibitor will come and bind here, and it will render the face of the enzyme unable to bind with the substrate. Allosteric inhibitor changes the enzyme's active site. Allosteric inhibitor competes with the enzyme's active site. This is completely wrong. So yeah, allosteric inhibitor is the one which comes and fits at a different site and alters the enzyme. Then for the coagulation of negative soul, leave it. Charges and soul, leave it. Hard substances. Hard substance melts at high temperature. Insulator in solid and molten state. So it cannot be an ionic solid, cannot be a metallic solid. Either it is a molecular solid or covalent solid. It melts at high temperature, so not a molecular solid, it is a covalent solid. Okay, this is a solid state question, but anyways, we have done this. All right, guys. So yeah, we are done with almost all the questions. We will continue with colloidal solutions in the next class. Thank you.